Thanks. I'll begin with a word of prayer. Dear Father, we thank you for this day. I thank you again for these students, and just ask you to bless this class, Lord. In your name I pray. Amen. Okay, so let me draw our thoughts together and stick a fork in this thing. You know what I mean? So we have been talking for a little while about Mobius transformations, which I would like to call fractional linear transformations because I think it's more descriptive, right? And so let us review what we know. So you could call them an FLT, a fractional linear transformation, right? So the basic definition is this. We have T. We can think of it as a mapping from the extended complex plane to the extended complex plane, where AD minus BC is not equal to 0, and the formula T of Z equals to AZ plus B over CZ plus D, right? So this mapping is a bijection, all right? So how does the map hit infinity in terms of terminology here? How do we output infinity in this wild new world of infinite math? Note the pole, all right, is what? CZ plus D equals to 0 gives what? Z equals to minus D over C is possible. The other possibility, right? The other possibility is that, in fact, the mapping is not like this, right? That the denominator is actually just a constant in disguise, right? In which case, this reduces to a plain old linear, or you could say a affine transformation. The affine transformation maps infinity to infinity, right? And in there is also the case that we could have the identity transformation, right? We got sucked into a conversation that led us down this path. We figured out, oh, sometimes these aren't honest-to-goodness rational functions. They're really just polynomials, first-order polynomials in Z in disguise, right? If we put the C equals to 0 and the D is non-zero, we reduce to just a linear transformation. Which is good because that means that the identity transformation's in there. So this is something we learned. Now, there's a few other facts. Not all. Yes, Sam?
I forget. Is AD not equal to BC guaranteed that we don't have 0 over 0?
That just means that it's not constant. If AD minus BC was equal to 0, the derivative is everywhere 0, which means it's a constant function.
Right, but does that also guarantee that we can't have 0 over 0 so that like we take enough properties?
Well, I think if we have 0 over 0, the understanding is that we fill in that 0 with the continuous, like we continuously extend for that formula. So, you know, let's see here. But I don't know if that can actually happen given the constraints AD minus BC not equal to 0. Can I actually have 0 over 0? I don't think that can happen. I mean, if I have A equals C and B equals D, then I basically have CZ plus D at top and bottom. But then, I mean, that would give me 0 over 0 at the quote-unquote pole, which is not a pole. It's just a hole in the graph, you know? But that cannot happen because we're assuming AD minus BC is non-zero. I'm going to go on. So here's some results, that some of which we've proved and some of which we could prove if I had been a better steward of our time. One is that if T1 and T2 are fractional linear transformations, then they're composite. T1 composed with T2 is also a fractional linear transformation, right? 2, which is that if we take T of a circle, or if we take T of a line, right? If we look at either one of those things, what do they output? Either a circle or a line, right? Every circle either maps to a line or another finite circle under a fractional linear transformation, and the same is true for a line. So if we have the understanding that lines are just circles through infinity, if you're willing to think about generalized circles, we can just say that a fractional linear transformation maps generalized circles to generalized circles. 3, T is conformal everywhere except possibly where? At its pole. I say possibly because some of the, there are linear transformations, fractional linear transformations, which do not have a pole, right? The affine ones, the linear ones, they do not have a pole, except at infinity. Infinity maps to infinity. So you could say the pole is at infinity if you like. And I would also point out something, that this conformality actually, if you think about it, really implies that the interior maps to the interior. Let me try to give you a geometric explanation of that. Let's see if we can understand something for a second here. So if I have, this is my region, yeah, S, and I look at some fractional linear transformation T, and whatever it maps to, I don't really want to, whatever. Not doing it justice, but this maps to that, right? And if we think about, I'm gonna look at finite regions just to keep the conversation relatively simple. So if we're going to orient S, so over here is T of S, right? And if we were going to orient S in the standard way, we would want the boundary to go around it counterclockwise, right? Because if we go counterclockwise, if you imagine a little dude or dudette, let's not be, yeah, right. You've seen the, okay, yeah, I can't say those things. Okay, because they'd be allowed to say in this year, but suppose for 10 years in the future, I could go to jail. Who knows, right? So if we go that way, then the interior to S is on our left, right? Correct? So if we pick, if you pick a point, say this one, Z0, and you pick another point in the interior, say Z1, you could study a couple different things, right? You could study the tangent to Z0, which would look something like this, right? And you could study the point that points from Z0 to Z1. And if you think about the image over here, wherever, I don't know, this is just a heuristic, but suppose that this is T of Z0, right? And over here is T of, my point is T of Z1 has to be there. If you think about it, I'm not sure this is actually proof, it's just a kind of a, what's the word, some kind of intuitive argument. Then, anyway, the conformality says that this angle theta has to be equal to that angle theta. And you can do this with more than just one point. You can do it with a bunch of points. And I think if you start thinking through that, it forces the interior to map to the interior. In the sense that, the orientation of the boundary is preserved. So I'm saying that suppose that this is the boundary of S is this counterclockwise oriented thing. So I would say that the boundary of the image, all right, should be the image of the boundary, right? So we have that. And I think those things come in part because of this conformal condition. Now you got to be careful. It could be that it gets turned inside out. Like the reciprocal map is a possible possible fractional linear transformation. We can have this situation, right? We can take this, map through the T of Z equals to 1 over Z map. We can map that to this, right? But it's still the case that the boundary, so here, counterclockwise, wait a minute, counterclockwise, right, has to get mapped to, if this is inside, right, then, let's see here, clockwise, this boundary. Well, clockwise, See, clockwise is the positive orientation for that region because as you go around the boundary, the region's on your left, right? That makes that a positive orientation. So clockwise is the proper orientation for a hole, whereas counterclockwise is for an edge in the plane. And so my larger point, though, is if you could pick different points in the region and study how the angle between the vectors which connect them transforms. And I think you'd be able to see that it has to map inside out by studying the angles preservation. I think you could prove this. I was thinking about this. I mean, this is just a fuzzy argument at the moment, guys, but anyway. All right. So my larger point is that fractional linear transformation maps the interior to the interior, and it maps the boundary to the boundary, and it maintains the orientation as it ought to, all right? But there's another point, which we proved last time, which is, a little bit more surprising. For T is uniquely fixed by its action on a distinct triple of points. So we proved that last time by, we gave an explicit argument to prove that if you fix 3 points on a fractional linear transformation, then it has to uniquely describe the transformation. Right? I actually gave you a pretty concrete argument for that, right? We just proved that if we had 2 of them and we look at the composite of their one with the inverse of the other, then we have a fractional linear transformation because of part 1, and also that the other thing I should mention, T inverse is also an FLT. All right. So then the composite of the mapping with its inverse is a fractional linear transformation which fixes 3 points, and thus it must be the identity mapping, because we proved that if a fractional linear transformation fixes more than 2 points, it has to be the identity transformation, which is probably something else I should add up here. Yeah, the identity is an FLT. Now, this is not for this list of 3 things here is not really for this class. Point number 1, if you look at all 3 of those things, if you're in abstract algebra, you can identify that, in fact, the set of all fractional linear transformation forms a group because it's closed under composition and inversion. And it's got the identity, so it's not empty. Yeah. So I may be solving a future abstract algebra homework for you right now, which is just adding insult to injury for those people who are not in here, right? But yeah, don't tell them about this lecture. This is our secret. So, yeah. Now, the larger there's another way you could argue, though. If you look at Nagel, Saff, and Snyder, which is that monstrous PDF that I scanned for you, I don't expect you to read all that. You can just kind of scan through it, take what you want from it. It certainly does have a sort of, what's the word, relaxed and sort of lackadaisical development of Mobius transformations from base principles, starting with translations and rotations and magnifications and inversions, oh my, put them all together, and then the definition, blah, 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 and all sorts of applications to other things, like the Smith chart in electrical engineering, which is interesting. It's apparently the only conformal map which is patented under U.S. patent law. So this is something called the Smith chart. It's useful for looking at the impedance of circuits, but it's really just the conformal map of a particular complex function. Anyway, he argues there, though, you don't find the argument I gave to you guys last time is actually from Fisher. So in Fisher, he's got a section, I forget what it is, but oh, this one. Yeah. So Fisher, where is section 3.3 actually has the argument I gave you guys about the distinct triples, right? That's from actually around page 200 of your text. So like I got that argument from Fisher, and I think it's a good argument because it was rather concrete. But there's another way you could argue, which is just that since the Mobius transformation maps circles to circles or lines to lines, and since it's uniquely fixed by how it maps a circle to a circle or a line to line, then you could use that as a way to argue that, well, I mean, that could be used to argue that T is uniquely fixed by its action on 3 points, because 3 points uniquely fix a line or a circle. I like the argument we gave last time, though. So, all right, so let's get through it. So here's some notation. So let's consider FLT, which maps a circle, let's say circle Z, which could be a line. Anyway, it's got the points Z1, Z2, and Z3 on it, okay? In that order, to the generalized circle CW, which has the points W1, W2, W3 on it. I mean, these are, of course, not the whole thing, right? So I could say it contains CZ and CW contain this triple of points. And I'm thinking of them as an ordered set of points, so that giving you these three points in order fixes an orientation for the generalized circle, right? It fixes a sense of where you've been and where you're going to, oriented curve. And then, so if I want to find the FLT which maps that to that, here's the technique that's used. You can consider, let's say, Z1, Z2, Z3, 0, 1, infinity, W1, W2, W3, like so. And all we need is we need to find a pair of maps. We need to find a T1. We can meet in the middle is the point. So we find T1 that goes Z1 to 0, Z2 to 1, Z3 to infinity. And I want to find a mapping T2, which does the same for the W's. So say T2, T2, T2. So if I can find two FLTs, T1 and T2, which do this, right? If I could find two things that do that, then if you look at it, we could basically use the following. Then if we let T equal to, well, T2 inverse composed of T1 will do nicely, right? Since if we look at T of Z, what do we get? Well, let's say T of Z1. What happens with T of Z1? T of Z1 would then be T2 inverse of T1 of Z1. What's T1 of Z1? T1 of Z1 by construction is 0. What's T2 inverse of 0? You just got to follow my arrow the other way, yeah? So T2 inverse of 0 is W1, right? Yep.
Is it always 0, 1, and infinity, or is that just what you chose in this case?
That's what I chose in order to justify the use of the cross ratio formula. You could send them to any distinct triple of complex numbers, just the same though. But then the formula for the meeting in the middle would not be the same. The meeting in the middle formula is the cross ratio formula, which I'm about to write down. I'll get to that in just a second. But my larger point here is that, of course, we could take this 1 and we could replace it with a j, right? And it wouldn't change anything because you can see that this is going to work for j equals to 1, 2, and 3, right? So it uniquely fixes these 3 points and thus is a unique fractional linear transformation that we want, the one we're looking for, the one that maps this 3 points to those 3 points, all right? And in that order. But here's the neat thing, is we can build T1 and T2 as follows. So this is a standard technique. This is called the cross ratio. Well, this itself is not the cross ratio. The thing I'm about to write is the cross ratio. But so T1 of z is by definition z minus z1 divided by divided by z minus z3. And then upstairs I've got I believe z2 minus z3. And downstairs I've got a z2 minus z1. All right, let me just take a breath here and see how this thing works, right? How does this work? So what happens when I plug in? See what happens when I plug in Z1? What happens? We get 0 over stuff, yeah? So plugging in Z1 maps to 0 as claimed. What happens when we plug in Z2? We get Z2 minus Z1, Z2 minus Z3, Z2 minus Z3, Z2 minus, hey, look at that. Since these are distinct, it's a distinct triple of points, these are non-zero complex numbers, and they just gone. So that simplifies, reduces to 1, right? And then, of course, if we plug in Z3, what happens? We get stuff over 0, which is understood to be infinity. That's the basic arithmetic of the extended complex plane, is that something finite over infinity, just infinity. I mean, something over 0 is infinity. Now, it's also possible to let one of these points be infinity. These formulas still have a natural interpretation if you let one of the points you're mapping to be infinity. You could do that as well. You just have to kind of use some common sense as to what that means, all right? So there's your T1. What would the T2 look like? So you got W minus W1, W2 minus W3, divided by W minus W3 times W2 minus W1. Same thing, but with W's instead of Z's. All right? And again, for the same reasons, it's going to map to 0, 1, and infinity. So my claim is that if we construct T as T2 inverse composed of T1, that's precisely the FLT, which takes that triple of points to that triple of points, like the Z's to the W's. And so if you look at that, so we want T of Z to equal to what? Is it T2 inverse of T1 of Z, right? In other words, we usually set that equal to W, right? The mapping we're looking at of Z is equal to W. This is our typical nomenclature for understanding a complex function of Z as it maps to W. So if I don't know what T is yet, right? To actually find the formula for it, the convenient thing to do here is just, one way to do it is just to take T2 of both sides, and that gives me, well, T2 of W equals to T1 of Z, right? Now, this right here, guys, is known as Z, Z1, Z2, Z3. This is a standard notation for that fraction. A standard notation for this fraction is W, W1, W2, W3. Notice the ordering of 1, 2, 3 matters. But, so this really is just saying set those two equal. This is the so-called method of cross ratios to find the FLT. So all you got to do then is write down those fractions and solve for W to actually find a specific one. Now, you'd probably like to see an example, right? Here's an example. So suppose I wanted to map this circle to this half plane. And this circle has the point 1 here. It's got the point I here. And it's got the point 1 plus I up here. What's that? Well, that would explain why I didn't like my results. Well, I now have solved the mystery of why I couldn't gain intuition for my calculation at the end. Thank you, Sam. Mystery solved. Anyway, so yes, that would be a better top point. Because the other point I just gave was what? That was the center of the pictured circle. And those 3 points are, I guess, on a different... Yeah. Oh well, anyway, so, Is there really a circle through any given 3 points? I can't believe it when I write that other point down. Like, what's the circle through these 3 points?
Draw through the origin and those three.
Yeah, it's the square sort of described.
Okay, I gotcha. Yeah, I couldn't see it in my mind's eye for a second there. Anyway, so I want to map the interior of this circle, all right, to this. All right, so the point is I need to pick 3 points that orient the circle in the appropriate way, right? So if I pick those 3 points that are pictured, what do I have? I've got, I got a counterclockwise, right? So it's got to go this way, right? So it's natural to think Z1, 1 plus 2i, Z2 equals to I, Z3 equals to 1. I mean, that's one way you could do it. And then over on the right half plane, trying to find this t, what do I want? Let's put, let's make 0 the first point. Let's make minus I the second one. Let's make infinity the third, just to be lazier than what I had. So I'm thinking of this, and would that make sense? Or am I going the wrong way? Yeah, I think I want to orient this way. That's the correct orientation. So, well, that's part of the point of this example, is that I can illustrate how that works, yeah. So, all right, so then we just set the cross ratios equal and try to solve for it. That should give us the FLT which does this. All right? So I need to say Z minus 1 minus 2I times, what is it? Z2 minus Z3, which is in this case I minus 1, divided by Z minus 1 times Z2, Z2 minus C1, excuse me, which is what? I think it's minus 1 minus I, yeah? And on the other side, I'm supposed to do W minus 0 times, well, what's it? Z2 minus Z3. So that's minus I minus infinity. Oh, what does that mean? And then, let's see here. Z minus Z3. Yeah. Oh, excuse me, W minus infinity. Whoa. How to interpret that? And then what's Z2 minus Z1, eh? Excuse me, W2 minus W1, which would be just minus I believe. I mean, I was hoping we could make sense of this together, but I could be wrong. It's possible. I'm already off my notes because of Sam's initial comment. I mean,
Didn't your notes use the same set of W points?
No, I use 3 finite points. Let's do that just to be lazy. I'll come back to this infinity thing in the next example. I want to look at, when infinity is involved, I want to look at it a different way, okay? So, I mean, there's an actually, when you use infinity as one of your points, there's something easier that can be done than the cross ratio. So what's another point that we could use instead of infinity? How about, yeah, minus 2i seems nice. So if we use minus 2i instead of infinity, that just changes these formulas a little bit. So we have plus 2i, yeah? And plus 2i here. Minus i. Right. So then to find the FLT, find t of z equals to w, you just solve the above. Which is straightforward, and you can do it. Right? Just algebra. All right. So it seems like at the end of every general technique you ever see in math, there's always the comment made by the instructor, and the instructor basically along the lines of, so this is totally general, right? It's a technique that solves every single possible problem of this type, except for the ones including infinity. Well, the ones including infinity, let's say there's some fine print I haven't quite addressed in here, but I think it is addressed in the PDF that I sent to you. He has formulas in the case that one of the points are infinity. He has different formulas in those cases. So I think what to do for the cross ratio in the case that one of the points is infinity is addressed in the handout from Staff and Snyder. But often the case though is I give you a simpler problem that doesn't actually require the full machinery of the cross ratio. And so if we're, for a specific problem, there may be an easier way to construct the FLT than doing the full cross ratio thing. And so I think this example serves to illustrate that, and it'll also just drive home the point of why we're doing this as it connects to solving Laplace's equation on weird spaces, which is the technique of conformal mapping, right? So here's the example. We want to map the unit disk, all right? Usual orientation, counterclockwise, yeah, to the upper half plane, all right? And so, and I'm going to choose, I need to choose 3 points. I need to choose 3 points on the edge of each in order to fix the particular fractional linear transformation I want to do it. So what I chose to do is -1, -i, and 1. Those are my points. And I'm going to map them to infinity, 0, and 1. So in other words, 1 maps to infinity, -1 maps to 0, and -i maps to 1. So I am actually not leaving you out to dry. I'm not leaving you out on a limb as far as dealing with infinity for an FLT. I'm showing you an example here how to handle it. Okay. I just would say the cross ratio is not the right tool. Yeah.
Is the map to infinity or negative?
Infinity. So it's not like that. I know. There is another use of infinity in this course. We do things like 1 plus infinity or 1 minus infinity. So the infinity that appears in something like this is actually a different concept than this one. I know. Yeah. Sorry about that. Like this one. That is a different concept of infinity than the one I'm currently using. I'm sorry. It just is. Okay, so I know it's maddening, isn't it? let's see here. So T of Z. So here's my point is you can use just basic tinkering to construct the formula. First of all, from 1, if I wanted to output infinity when I plug in 1, you know what we need? We need a pole. We need a pole at 1. How do you do that? You put z minus 1 in the denominator. So that's from 1. From 2, I want to map to 0. That's why I chose infinity and 0. We want to map to, if you can put infinity and 0 on the boundary of the curve you're interested in mapping to, that makes life much easier because 2, this says I've got a z plus 1 upstairs, right? Because if I put that there, that maps to 0 when I plug in 1, right? So at this point, if you're keeping track, all that's left is a multiplier in the front, right? We've got some complex number a that fixes the FLT. So to figure out the value for a, we just need that third point. So to fix a with 3. So 3 says that t of minus I is equal to a times 1 minus I over minus I minus 1, which is, by the way, equal to 1. So therefore, a is equal to minus 1 minus I over 1 minus I, which you can multiply by 1 plus I over 1 plus I, and that will give you minus 1 minus 2I plus 1, all divided by 2, also known as minus I. So in short, T of z is nothing more than minus I times z plus 1 over z minus 1. So, you know, yes, the cross ratio is fantastic. Yes, it solves all kinds of weird, rather arbitrary problems, but it comes at a cost, and the cost is this algebra. This is a non-trivial cost. We're talking about a cost of 10 minutes to a test to do this algebra reliably, safely, carefully. Maybe not 10 minutes, but 5 minutes. I mean, this is a significant investment of algebra time to solve this for W. In contrast, whoa, that's fast, right? That is really, really fast for this kind of problem. And there you have it. You can check that it works. And we can do more. We can rewrite this in terms of what does it look like in terms of x and y, all right? So you do the algebra, and what you'll get after just a minute or two is 2y plus I times 1 minus x squared minus y squared divided by x minus 1 quantity squared plus y squared. So this is what, you know, W, which is u plus iv, looks like, yeah? And all right, so check this out. Suppose I want to solve Laplace's equation, right? I want to solve Laplace's equation on the unit disk. And I want to solve Laplace's equation such that I have a value of 10 up here, and I want to have a value of phi equals 10 up here, right? And I want phi equals to minus 10 down here, yeah? Then I believe I can solve that pretty easily over here. If you look at the right half plane, let me suggest that we could use capital psi of w equal to, let me suggest 10 plus 20 over pi times arg w. Psi of w equals to 10 plus 20 over pi arg w, using the ideas that we talked about in the previous class, we can fit that. You can check it out. What happens when you plug in any point up in here? What do we get? We get psi, psi equals to 10 because the argument there is 0 of w, right? What's the argument? Oh, I'm an idiot. I meant to put, I think I copied that down wrong. Let's put a minus here, guys. I'm sorry. Minus. What happens when I'm on the other when negative w-axis, negative real w-axis? There I have a standard angle in the w-plane of pi, right? So pi's cancel. We get 10 minus 20. We get psi equals minus 10 over here, yeah? So then, to construct phi, how do we construct phi? All right, over here, we let phi of z equal to what? Equal to psi of t of z. That's the trick. This is the conformal mapping. And so what does that actually look like? Phi of z is what? Apparently 10 minus 20 over pi arg of that. 2y plus I times 1 minus x squared minus y squared divided by x minus 1 squared plus y squared. And there you have it. That's a solution to Laplace's equation on the unit disk, which gives you a value of 10 on the upper half and a value of minus 10 on the lower half. You can try it out. What happens in this equation when we go to the unit circle? Plug in the unit circle, what happens here? That piece goes to 0, right? You got a positive number downstairs, right? And so you're basically looking at either a positive or a negative real number, depending on whether you're in the northern or the southern half of the boundary of the disk. If we have a positive real number, its angle is 0. If we have a negative real number, its angle is pi, because this is the standard argument. And so this formula, again, either reduces to 10 on the upper half or minus 10 on the lower half. So this is the technique. And you can see, because we can map arbitrary circles to arbitrary circles, it allows us to transport that kind of solution to all kinds of crazy places in the plane. Anyway. So that's it. Next time we will start integrating. That is it. That is the end of the test 1 stuff. All right. And so, yep. You can, I think we're out of time.